Hi, my name is Scott Simpson, and today we'll be talking about hybrid orbitals. It may be a good idea to review atomic orbitals, which I do have a video for, so check out my YouTube page and you should be able to find it. Now, what is hybridization? Well, what happens is atomic orbitals overlap to create these new hybrid orbitals, and you can figure these out from the electron domain geometry. So, what we need to do first is talk about how these atomic orbitals overlap. So, let's look at an S atomic orbital, which looks like a big beach ball, and a P atomic orbital. So this will be an S, and let's look at a P orbital, which kind of looks like a dumbbell. What happens is there's a node at the center. Something along the lines of this. P. Or it may be better to draw it like this, since we have three of them. Probably be better. Like that. And it should be symmetric. Unfortunately, the way I've drawn mine is not symmetric. I apologize if it's difficult to see also, because I kind of have crummy markers right now. So what happens is when you add these guys up, they're not drawn exactly to scale, but you'll get two hybrid orbitals that look something along the lines of this, where you have the center where your atom is based, and they'll be exchanged on that side, and then one where it'll be like that. And then when you add those two together, you actually get something that looks like a dumbbell. Well, why does that happen? It has to deal with properties of atomic orbitals where they can be in phase or out of phase of one another. What I mean by that is if you look at their wave functions change sign. So if we assume that we always have a positive sign s orbital, we have a node at the center of our p orbital. And what a node actually is where the wave function changes sign. So we'll have a positive on this side and a negative on that side. What that ends up constructing, if we add these two together, positives are additive, positives and negatives cancel out. So we'd end up with an orbital that looks something along the lines of that guy right there. If we were to switch signs now, negative and a positive, they overlap, and we'd get something new that looks like this. And then when we add those two together, we end up with our hybrid orbital, which would be an SP type orbital. So this is also an SP, this is also an SP. But this is the overall hybrid orbital. So, what you can do is you can relate these hybrid orbitals to their electron domain geometry. And what I mean by that is you say that each domain site has a lobe associated with it. So you can make this handy dandy little table. So you have your E domain geo, so your electron domain geometry, and then you have a hybrid orbital that is formed. So in the case if we have something linear, that will be an SP type orbital. When we have something that is trigonal planar, it'll be SP2. We have something with tetrahedral, that will be SP3. Then if we go further, we can have, when we're looking at atomic orbitals that have D-like character, or atoms that have D-like character, for example, the transition metals or even stuff like sulfur, we can get trigonal bipyramidal structures, and they would have an SP3D hybridization. Then when we looked at octahedral complexes, we can have SP3D2 type orbitals. Alright, so let's go through a couple of examples of these to better illustrate this point. So let's look at a couple of molecules. So let's look at something like methane. So methane's pretty simple. has a structure CH4, which we know is tetrahedral. So if we were to draw this out with a Lewis structure, we would represent it in 3D space with those fancy bonds. And we'd end up with something like this. So the molecular geometry is tetrahedral. Tetrahedral, it's also shortened to TD. The electron domain geometry is also TD. So what that means is we have an sp3 hybridized system. Let's look at something like ammonia. I could write an N properly. NH3. So when we look at that, it's very similar to our methane, except we have a lone pair instead of a hydrogen. So we have a molecular geometry that should be trigonal, pyramidal, which translates to an electron domain geometry of tetrahedral. So remember, the electron domain geometry is the important point. So this would also be sp3 hybridized. So let's look at another example. Let's look at formaldehyde. So formaldehyde has a double bonded oxygen to it, and it has the molecular formula CH2O. So we're looking at formaldehyde CH2O, like that. If we draw the Lewis structure, we end up with a double bonded oxygen. It looks something like this. So our molecular geometry is trigonal planar, and our electron domain geometry is also trigonal planar. So that means we have an sp2 hybridized system. All right, what about something like so boron trifluoride, where we have 3 fluoride ions? It would look something along the lines of this: B, F, F, F. This one also has a trigonal pyramidal molecular geometry, and the electron domain geometry is also the same as trigonal pyramidal, or I mean trigonal planar. Which then translates to an sp2 hybridized system. So I hope I've been clear in demonstrating what are hybrid orbitals, how you can figure out what the hybrid orbital is of a system. A quick run through: you need to know the Lewis structure. Once you know the Lewis structure, you need to know the molecular geometry, and you need to know the electron domain geometry. The electron domain geometry being the more important of the two, because you can determine what hybridization you have in your system if you have just s orbitals mixing in 1p, if you have more than 1p, and so forth. So I hope this has been instructive. If you have any questions or comments, please leave them below or send me an email. Thank you very much, and have a great day.